All right, good afternoon, everybody. Today we are going to continue to discuss our asteroid mining example. And today we are going to focus on two things. One is to how to compute a confidence interval of our Monte Carlo estimate. So this is very important because you can use arbitrary number of samples to compute your Monte Carlo result. You can use one sample, or you can use 1,000,000 samples. However many number of samples you use, you're going to get your answer. What's the difference? The difference is really in how confident you are with your answer. If you use only one sample, you're not very confident on the answer you get. If you use 1,000,000 samples, you are likely more confident on the result you compute. So today we are going to quantify how confident you are on the answer you get using Monte Carlo methods. All right, so to remind everybody, we are going to continue on the asteroid mining example we started on Monday. The problem is we have a spacecraft approaching an asteroid at a given 250 meters per second. We have to decide how far away from the asteroid we should start firing our solid fuel rocket. And the amount of delta V the motor gives us and the burning time is two random variables we consider over here. If the solid motor is not able to decelerate us to speed of 0, we have to use a much smaller cold gas thruster to decelerate us. And the problem is to determine if you start decelerating at a given distance, how likely are you going to crash? Right? Okay. So last lecture we coded up a short computer program which I copied over here. It's called the crashed. That's going to compute the probability that we crash into the asteroid. And here, the probability is computed given x0, the position at which we start firing the motor, the dv and t, which are a number of samples of the delta V produced by the solid rocket booster, and the firing time of the solid rocket booster. Right? We started some procedures to sample the delta V and t and compute the P crashed. So now let's start answering the question today. First of all, how do you think we should quantify the level of confidence we have on our result? So if you are an engineer, you coded up this program to compute the probability of crash, and another person wants to actually implement this procedure, and of course a natural question is, how sure are you with the result? If you compute a probability of let's say 1% of crash probability, I'm going to ask you, how sure are you about this 1% number? How would you answer that? Replicate the experiment many times. That's a very good suggestion. So let's actually try it to see what we get. Okay.
When you say 1%, you have to give also like a plus or minus whatever, because it's a continuous variable.
So if you give 1%, you also have to give plus minus whatever, because you are right. Usually when you give a result, no matter computationally or experimentally, you always want to give a result plus minus something, right? But the reason you cited was what? What was the reason you cited?
Because it's a continuous variable.
Because what is a continuous variable?
Well, or not the result, like the problem, like the crash. So like the crash probability is a continuous variable.
The crash probability is actually not a continuous variable, it is a random variable.
Or it's a continuous random
x0 is continuous.
The plus minus is the confidence.
the plus minus is the so x0 is a continuous variable, but that doesn't matter, right? So I'm basically, your answer is, if I started my deceleration at a certain x0, what is the likelihood of crashing? Right? Huh?
I guess what I was thinking is that because x0 is a continuous variable, the integral of the probability density function around any value is 0, so you have to give the plus or minus range. Where if x0 was discrete, you could say there's sort of finite confidence in it being this particular discrete value, because that covers sort of the integral over your variable of interest.
Okay, so I don't think I understand what you are saying. So we're estimating the probability of a crash. If condition on if we start the deceleration at the fixed x0. So what I was saying is that it matters if x0 is discrete or continuous.
I think I misunderstood your question.
I think so you're saying, okay, you give an answer to the question of let's say the probability is 1%.
Yes.
And so if you want to say how confident you are that the probability of crash is actually 1%, then that would be 0, because you need an interval.
Oh yeah, okay, yeah, that's right. So okay, yeah. So how confident are you that the probability is exactly 1%? You're right. It's actually 0, right? Because it's actually unlikely your computed number is actually the exact answer, right? So the question I was asking in some sense is ill-posed, right? So a well-posed question is that instead of giving me a number 1%, you should give me an interval of numbers. And then my well-posed question should be, for example, if you give me saying that the crashing probability is somewhere between 1% and 2%. That's a more reasonable answer that allows me to ask the well-posed question. How confident are you that the crashing probability is between 1 and 2%? Right, so now we have a well-posed answer from you, and that enables me to ask a well-posed question. All right, so then how would you answer that now well-posed question? If you give me an interval of probabilities, and I'm going to ask you, how confident are you that the probability actually lies in your interval? Yeah, so we get 2 answers of repeating the experiment. So let's actually try something to repeat the experiment to see what we get. All right.